Le Chatelier's principle is when a reaction shifts to relieve the stress that is applied. A stress is a change to the conditions of a reaction, and there's 3 different ways that we can apply a stress. We can apply a stress by changing the concentration, by changing the pressure and or volume, and by changing the temperature. Concentration. If you add more of a substance, then you're going to shift to the opposite side of what it's on. If you remove a substance, then you're going to shift towards the side that it's on. Now, pressure and volume are inversely related based on Boyle's law. So if you increase pressure or decrease volume, you're going to shift to the side with less moles of gas. So you're only worried about gases when you talk about pressure and volume. If you decrease pressure, then you're increasing volume. So you're going to shift to the side with more moles of gas. If you change temperature, you will actually change the value of K. So K is the equilibrium constant for a specific reaction, and it will always remain the same unless you change the temperature. So temperature is treated the same way as concentration is. So if you increase temperature, you shift away from it. If you decrease temperature, you shift towards it. An endothermic reaction has the heat or temperature on the reactant side, and delta H, or the change in heat, is a positive value. Exothermic, heat and temperature are on the product side, and delta H, or the change in heat, is negative. So use Le Chatelier's principle to predict how each of these changes would affect the ammonia equilibrium reaction. So if you remember, the left are your reactants, and the products are on the right. So if I'm removing hydrogen, hydrogen is H2, and for this reaction, hydrogen is a reactant. Now when I remove a substance, I want to shift to the side that that substance is on. And since hydrogen is a reactant, I'm going to shift left. Now the question might also ask about the concentrations of the other substances in the reaction. So what happens to the concentration of nitrogen if I shift to the left? Well, because nitrogen is on the left, it would increase its concentration. NH3 on the right would decrease because I'm shifting away from it. Adding ammonia. Ammonia is NH3, and in this problem is a product. When I add a substance, I want to shift to the opposite side that the substance is on. So if I'm adding the product and that's on the right, I'm going to shift left. And if I shift left, then N2 is going to increase because I'm going towards it, and H2 is also going to increase because I'm shifting towards it. Now adding hydrogen. Again, hydrogen H2 is a reactant for this problem. I'm adding the substance, so I want to shift away from it. So since hydrogen is on the left, I'm going to shift away from it and shift to the right. That means the concentration of nitrogen would be decreasing and the concentration of NH3 would be increasing. How would decreasing the volume? Another way of saying decreasing the volume is to say increasing the pressure. Well, when we talk about pressure and volume, we want to talk about gases. So you're only worried about the ones that have the G next to it. So you add your coefficients together, 2 plus 1. That means I have 3 gases as a reactant versus 2 gases as a product. So if I increase pressure or decrease volume, I want to shift to the side that has fewer moles of gas. So I'm going to shift to the right. That would mean SO2 would decrease, O2's concentration would decrease, and SO3's concentration would increase. In problem B, I have 1 plus 1, so 2 moles of gas as a reactant versus 2 moles of gas as a product. So increase pressure, decrease volume, I want to shift to the side that has the fewest. Well, here I have a situation where they're equal, so there's actually no shift that would occur. In problem C, I actually don't have any gas on this side because NOBr is a solid, versus 2 plus 1 to make 3 gases. So increase pressure or decrease volume, I'm going to shift to the side with the fewest moles of gas, which would be 0. So I'm going to shift to the right. So what happens to the concentration of NOBr? Nothing. Because it's a solid, nothing is affected. The concentration of NO would increase, and the concentration of Br2 would also increase because we're shifting towards them. In the following equilibrium, which way would you shift if temperature was decreased? Another way of saying temperature decreased is by saying that it was cooled. So what happens to the concentration of the products? Well, if we look at the first one, it gives us a delta H value of negative. Don't worry about the number or the units. The negative delta H tells me that this is an exothermic reaction. So that heat is actually a product. So we can put plus heat or plus temperature as a product. So if I decrease temperature, I'm going to shift away from temperature. If I decrease temperature, I'm going to shift towards the temperature. The temperature is a product, so I'm going to shift to the right. What happens to the concentration of the product? So CH3CHO would increase. Now changing temperature also is going to change the value of K. Well, I'm shifting to the right, which means my forward reaction is favored. So K is going to increase in value because the forward reaction is favored. In letter B, I have heat as a reactant. So this is an endothermic reaction. If I decrease temperature, I'm going to go to the side that heat is on, so I'm going to shift to the left. So the concentrations of my products, CaO doesn't matter because it's a solid. CO2 is going to decrease. So what happens to the value of K? K is going to decrease as well because I'm shifting to the left, which means the reverse reaction is favored. In the last problem, heat again is on the product side. So this is an exothermic reaction. If I decrease temperature, I'm going to shift to the side that it's on. So I'm going to shift right, which means the concentration of NO is going to increase. The concentration of H2O is going to increase. And my K value is going to increase because I'm going to the right. The forward reaction is favored.